So this hour is going to be just about tons and tons of examples of using L'Hopital's rule. And I was asked to mention, so there's no dispute that L'Hopital's rule is called L'Hopital's rule. That's kind of a worldwide, accepted worldwide. However, there is a dispute whether it is correctly attributed to L'Hopital or to his students. Someone mentioned here the Bernoullis. So I'm not going to get into those kind of historic issues. We're going to call it, like everybody, L'Hopital's rule. Okay? Okay, so example number 3. Suppose we want to calculate the limit as x goes to infinity, which is fine. 5x squared minus 3x divided by 7x squared plus 1. Now this is an example. This is an example of a situation where the top goes to infinity and the bottom goes to infinity. So this is an infinity over infinity situation. This is an example that you knew how to solve in your pre-L'Hopital life. You just divide top and bottom by x squared and you're going to get 5 over 7. Do you agree? But you're in a different phase of your life. You're going to see a limit and you're going to want to hit it with L'Hopital. Okay? And that's fine. You can do it the previous way. It's just as short and elegant. Or you can do it using a much heavier machinery because you're using derivatives, which are defined via limits of those expressions, remember? So, but both are fine. So what does L'Hopital tell us? Well, take the limit of the quotient of the derivatives. So what's the derivatives here? It's 10x minus 3 divided by 14x. It's still an infinity over infinity situation, so we're going to actually use L'Hopital again. And we're going to get the limit as x goes to infinity of 10 over 14, and now we're finally done. Okay, so this is an example where L'Hopital does not help us do something we didn't know how to do before. And it's not easier or harder, it's just a different way of doing it. Okay? Now note, let me emphasize here, that once we found that this limit exists, that justified saying that this limit equals to it. That's the third part of the conditions of the theorem, that the limit of the quotient of the derivatives exists. So once I know this limit exists, that justifies saying that these two are equal. Okay? Is this clear? Is it clear what I'm trying to say here? Okay, so you're actually justifying the third condition only after you've calculated it. Okay? Example 4. Let's take the limit as x goes to 0 of sine x minus x divided by tan x minus x. As x goes to 0, sine goes to 0, tangent goes to 0, so this is a L'Hopital 0 over 0 situation. So saying that this equals to this, is not obvious to the reader what you were doing here if you don't justify what you were using here. If you just write this equals this, huh? If I were to write this last week, you would say, huh? Right? Where did it come from? How did I suddenly, what did I cancel here? What did I divide here? What kind of algebra did I do? It's not. It's taking the derivative. It's using this theorem. So yes, you have to justify it. This specific way of justifying it by writing LH 0 over 0 that's what I'm used to. If you want to write it differently, that's fine, as long as it's clear what you're using and why it's legitimate. Okay? So what do I do here? I take the derivative of the top divided by the derivative of the bottom. So the derivative, and again, don't forget, not the quotient rule. Derivative of the top is cosine x minus 1. Derivative of the bottom, what's the derivative of tangents?
1 over cosine.
Right, 1 over cosine squared. we're not going to use secant and cosecant. We mentioned that. It's the same, but okay. So we get this. Do you agree? Once again, it's a 0 over 0 situation. Cosine goes to 1, so the top goes to 0. Cosine goes to 1, so the bottom goes to 0. So it's again a 0 over 0 situation. And again, you don't have to do L'Hopital here. You can do a common denominator here. You'd get something of the form 1 minus cosine squared, which you can break algebraically into 1 minus cosine times 1 plus cosine. The 1 minus cosine is going to cancel. You can carry this out without L'Hopital. We're doing examples of L'Hopital, so let's do L'Hopital. Okay? So, again, this is a 0 over 0 situation. So this equals limit x goes to 0. The derivative of cosine is minus sine. The derivative of negative 1 is 0. So that's all that we get from the top. What about the bottom? So this is cosine to the power negative 2. Do you agree? I'm taking the derivative of the denominator. So what I have here is cosine to the power negative 2. The derivative is negative 2 cosine to the power negative 3, which I'm going to write as 1 over cosine cubed, times the inner derivative. There's a chain rule here. So what's the inner derivative, the derivative of cosine? Negative sine. So I have to multiply this by negative sine. Do you agree? And now these two cancel, the minus sign here and the minus sign here. And I get just this limit. So what's the limit? As x goes to 0, cosine goes to 1. So the limit is minus 1/2. Okay? And I do recommend trying to do this. This is less trivial, a bit less trivial. Try to do this without L'Hopital. Okay? So that's another example. Let's leave the theorem and let's write some more examples. So example number 5. Example number 5. So suppose I want the limit as x goes to 0 of sine x over x cubed. So we argue, it's okay to use L'Hopital, to do iterations of using L'Hopital, that's fine. Okay, you do the second iteration, that justifies the limit of the derivatives, which in turn justifies the limit of the original quotient. Okay? Okay, suppose we want to do this. Limit x goes to 0 of sine x over x cubed. So this is again a L'Hopital 0 over 0 situation. Right, so I'm going to write limit x goes to 0. The derivative of sine is cosine. The derivative of x cubed is 3x squared. I'm going to use it again, so it's the limit x goes to 0. The derivative of cosine is minus sine, divided by the derivative of 3x squared, which is 6x. I'm going to use it again, so it's limit x goes to 0. The derivative of minus sine is minus cosine. The derivative of 6x is 6. So the limit is minus 1 over 6. Good? No. No? Why not? Right. I lied. So where's the lie here? Right. Cosine x goes to 1. This is not, this point, this is a lie. This is a ugly, ugly, mean, heartless lie. This is false. I got some of you, right? Cosine x does not go to 0. This is not a 0 over 0 situation. You cannot use L'Hopital here. The conditions of the theorem do not hold. Right? Look at the theorem again. You have to be in a situation where both f and g go to 0, or we set infinity. Okay? Clear? So you can't just pull L'Hopital whenever you want to. That's false. Okay, so here, big mistake. Yeah, mistake would be kind of, you know, big crime. Crime, I like. Big lie. Okay, you cannot use L'Hopital there. It just doesn't hold. And you can't use theorems in math when the conditions don't hold. You get nonsense. Okay? Example, here's the nonsense. So how would we do this? How would we do this without lying? How would we do this honestly? Well, the first step is kosher. The first step is okay. Right? Here is where you would go wrong. But what's the limit of this thing? Cosine goes to 1. X squared goes to infinity, so the product x squared goes to 0, sorry. So the product is infinity. Okay? And you could do this straight away. So you could write from here instead, you could just write limit x goes to 0 sine x over x times 1 over x squared. This goes to 1, we know. As x goes to 0, 1 over x squared goes to infinity. So the limit is infinity. Without L'Hopital at all. Okay? So this is a word of caution. Be careful. Okay? Be careful when you use L'Hopital, just to verify that the conditions hold. You can't, and it's not just about L'Hopital, but with L'Hopital, it's kind of tempting to do these mistakes. It's kind of tempting to just apply L'Hopital without thinking too much, and you can get into trouble. Okay? More examples. More examples. So this would be example number 6. Example number 6, how about the limit as x goes to infinity of x divided by root x squared plus 1? So do you agree that this is an infinity over infinity situation? Right? The top goes to infinity, the bottom goes to infinity. So I'm going to encode that as before by saying L'Hopital infinity over infinity. What do we need to do? We need to take the derivatives. So I'll take the derivative of the top. You guys take the derivative of the bottom. Just splitting the work. Okay, so this is x squared plus 1 to the power 1/2. So it's 1/2.
The derivative is x squared plus 1 times x.
So x squared plus 1 to the power
Negative a half.
-1/2. So let me write it in the denominator instead of, so it's this. Right, 2x. And these 2's cancel. Okay, let's rewrite this. So here I'm not doing L'Hopital, I'm just rewriting it. The 2's cancel, and instead of dividing by this, I'll multiply by the reciprocal. So it's limit x goes to infinity, root x squared plus 1 divided by x. Good. Do you agree? Okay. This is still an infinity over infinity situation, right? What do? Well, we know that iterations might help. So let's do L'Hopital again. Limit x goes to infinity. The derivative of the bottom is 1. See, you complained about me taking the top previously, so I'll take the bottom this time. What about the derivative of the top? Right, but that's not hard. Well, it wasn't hard in the first place. So what do we get here? We get x over root x squared plus 1. And instead of dividing by 1, let's not do anything. So we get this. So what do? Divide
by x.
We do L'Hopital again, right? It's still infinity over infinity situation, right? Okay, no, we don't do L'Hôpital again. Okay, if you weren't convinced here, now you should be convinced that, well, we didn't make any progress in this example. Okay, so this example is here to convince you that nothing failed in the conditions of L'Hôpital. Okay, we can use L'Hôpital, it just doesn't help. Okay, so sometimes L'Hôpital is useless. Okay, and by the way, you only really see that it's useless here. Sometimes taking reciprocals is going to make it work. So it's not exactly true to say, hey, we could have stopped here and given up on L'Hôpital. Okay, we'll see an example. Example 8 or 9 will be an example of such, where you take the reciprocal and suddenly magic happens. Okay, but here, this is when you should give up. Okay, you just got back where you started. Okay, so what do we do? So instead, so let's write here that L'Hôpital is simply useless in this example. It's not that the theorem fails. It's not that we made a lie using it where the conditions don't hold. It's just that it doesn't help. Okay? So what do we do? Well, we go to our pre-L'Hôpital life, which we shouldn't forget, and write this equals this original limit. You can divide top and bottom by x, as somebody suggested correctly. So we get limit x goes to infinity. Dividing top and bottom by x, I get 1 over. Instead of dividing by x, I'm going to divide by root x squared. So putting that x under the root. So I'm going to get the quotient of x squared divided by x squared, which is 1, plus 1 over x squared. Do you agree to this step? And when x goes to infinity, x squared goes to infinity, 1 over x squared goes to 0, 1 plus something goes to 0 goes to 1, the root is 1, so the entire limit is just 1. Without L'Hôpital. Good? Questions? Okay, example 7. Example 7, limit x goes to 0, x squared sine 1 over x divided by sine of x. First of all, do you agree that this is a 0 over 0 situation? Why is that true? The bottom goes to 0, obviously. What about the top? Right. It's a bounded function times a function that goes to 0. The product is 0. Goes to 0. Right? So this is a 0 over 0 situation. Let's do L'Hôpital. So limit x goes to 0. Bottom, the derivative is cosine. What about the top? So, in fact, this is similar to the function I gave you in the previous hour to try the showing that its derivative is not continuous. So there's a product and there's a chain rule hidden here. So it's the derivative of this, 2x times sine of 1 over x, plus x squared untouched, and now the derivative of sine of 1 over x, which is cosine of 1 over x, times the inner derivative, which is negative 1 over x squared. Does everybody feel comfortable with this and with the speed I did it? Okay, you should by this point. You should feel very comfortable with taking derivatives and doing them without being intimidated or slowed down by them. Okay? So, what do we get? The bottom goes to 1. So this is a non-issue here. What about the top? There are two factors here. This factor goes to 0. Because again, it's x which goes to 0 times sine of 1 over x, which is bounded. Do you agree? What about this thing? These two cancel. Do you see that? These two cancel. Well, the minus survives, but that's not a big deal. And what about cosine of 1 over x? It doesn't have a limit. It behaves exactly like sine of 1 over x. It's this accordion phenomenon. Right? So this thing does not have a limit. Therefore, the entire thing doesn't have a limit. Because if the entire thing had a limit, you could subtract this, and it would say that this has a limit, but it doesn't. So the whole thing does not have a limit. What does that mean? Cosine of 1 over x behaves just like sine of 1 over x near 0. Same picture. Okay, so I'm not going to prove again that it doesn't have a limit. It's exactly the same phenomenon. You could easily convince yourself by looking at what we argued there. You can do highness sort of arguments or whatever. So this doesn't have a limit, and therefore the whole thing doesn't. Because if the whole thing did have a limit, you could write this as the whole thing minus this part that does have a limit, and you'd get that this does have a limit. Okay? So the whole thing does not have a limit. What does it mean? Right. It doesn't mean, so let me write this, so here, limit does not exist. No limit for this thing. Limit does not exist. This does not mean, does not imply that the original limit does not exist. It does not imply that. Because the theorem said, if this limit exists, then it's equal to this one, and this one exists in particular. It didn't say that if this limit does not exist, then this one does not exist, and that's not true. Okay? So as a matter of fact, if we try to do this pre-L'Hopitalishly, right, so we'll rewrite this. Limit x goes to 0. Let's write it as x over sine of x times x sine of 1 over x. I distributed the x squared 1/2 for here and 1/2 for here, or 1x for here and 1x for here. This, we know, goes to 1 as x goes to 0. This goes to 0 as x goes to 0, because this is bounded times x, which goes to 0. So all in all, what is this limit? 0. So the original limit does exist. It's much easier not to even get your hands dirty with L'Hopital. And still, you're likely to just L'Hopital everything, when L'Hopital is also a verb. Okay? So you're likely to L'Hopital it when you're going to encounter things like this. Okay? Questions about this example? Good? Okay. Example, wait, what number example was this? 5, 6, this was 7. Moving on to 8. So let's leave the theorem. So we saw all kinds of, the 3 previous examples are kind of not examples, they're non-examples. They're various, or 4 previous examples. They're examples where actually you want to not use L'Hopital. First of all, because you don't want to use L'Hopital with mistakes, by doing L'Hopital when it's not a 0 over 0 or an infinity over infinity situation. Second of all, you don't want to do L'Hopital when you get into a, the limit of the derivatives. You're not in any better situation where you started. It's not easier to find. And you're not going to want to do L'Hopital when the limit of the derivatives doesn't exist and the theorem doesn't hold, and you have to do something else. Okay, so L'Hopital isn't magic. It's a tool. It's a very useful tool. But it's not a magic tool that from now on you don't have to worry at all about calculating limits of any sort, because they're just, you're always going to do L'Hopital and get it over with quickly. Not the case. Okay, another example. So example 9. Suppose we have 8. Sorry, 8. You're right. Suppose we have... Do you know how to make an 8 into a cat?
Sure.
8. It's looking the other way. Sorry. Where were we? Oh, sorry about that. Okay, so suppose I want to do the limit as x goes to 0 plus of x ln of x. So when x goes to 0 plus, x goes to 0, ln of x goes to what? Right? ln of x looks like this, having the y-axis as an asymptote. Do you agree? So do you agree that this is a 0 times minus infinity situation?
Yeah.
Okay? Can we do L'Hopital 0 times minus infinity? There's no such thing, right? But standard, very standard procedure, limit x goes to 0 plus, rewrite it as ln of x divided by 1 over x. That's the same thing, right? And now it's an infinity over infinity situation. Well, a minus infinity over infinity situation. Do you agree? Okay. So now we can apply L'Hopital. And I just rewrote it. I just took the reciprocal of one part. Okay. So now we can use L'Hopital infinity over infinity. And we get the limit, x goes to 0 plus, the derivative of the top, 1 over x, derivative of the bottom, negative 1 over x squared. I can cancel things out here, so I get the limit as x goes to 0 plus of what? Minus x, so the limit is 0. Do you agree? Everybody? Okay, so very standard. So now this is the first of a bunch of examples that are going to show us how to convert other limits which are undefined, like 0 times infinity. So maybe let's write it here. This is an example of 0 times infinity, of course in quote marks. How to convert them into a L'Hopitalable situation. Okay? Example 9. Limit x goes to 0 plus of x to the power x. So this is something of the form 0 to the power 0, which is again an undefined limit. How do we handle it? Again, a very standard move. Standard, I don't want to even call it a trick, but you can call it a trick. So I'm going to rewrite this. Limit x goes to 0 plus. I'm going to write it as e to the power ln of x to the x. E to the power ln is applying a function and then its inverse function. That's not like doing nothing. Do you agree? It's like taking the root of x squared, or taking sine of arc sine, right? So do you agree that these things are equal? But now, once I put this exponential sort of thing into a logarithm, I can pull this x as a coefficient. Do you agree? So this is the limit as x goes to 0 plus of e to the power x ln of x. Right? So these are just rules of logarithms. And now I have e to the power something of the form 0 times infinity. And I can do standard things in order to L'Hospitalize this thing. But I don't need to, because that's exactly example 8. Do you agree? This is precisely example 8, which is there just by sheer coincidence. So what do I get? I get, so this goes to 0. So here the limit is e to the power 0, which is 1. So this is by 8. Hmm?
Any simple exponential function always passes at 0 through 1.
Any simple exponential function?
Yeah, like 2 to the x, 3 to the x, 4 to the x, 5 to the x always passes through 1.
Yeah, but this is not the situation here. This is...
No, but it's an exponential function.
No. This is also a polynomial function. It's x to the some power. Right? This is not... If x was fixed, you would be correct. Okay, but this is not the case here. So you have to be careful when you do things of this form. Okay, this a priori, this is an undefined situation. You have to solve it using some tools. Okay. Example number 10. Example number 10. Let's look at let's look at the limit as x goes to 0 plus e to the 1 over x divided by 1 over x. As x goes to 0 plus, 1 over x goes to infinity. E to the 1 over x also goes to infinity. So this is an infinity over infinity situation. Do you agree? Everybody? So this is infinity over infinity. We call L'Hopital to our aid. We have to take derivatives. So it's the limit, x goes to 0 plus. The derivative of the bottom is negative 1 over x squared, right? The derivative of the top is what? So e to the something is just e to the something times negative 1 over x squared, the inner derivative. Do you agree? Right? And this limit, well, these two cancel. As x goes to 0, the limit is infinity. Do you agree? Good? Okay, this wasn't that tricky. I want to take it a step from here. So I'm going to give two examples. One, suppose you want to do the limit as x goes to 0, let's do 0 plus, of e to the minus 1 over x squared divided by x to the power, let's say, 100. Again, this is a 0 over what? Yeah, this is a 0 over 0 situation, because as x goes to 0, this goes to 0. And here, because of this minus, so this goes to infinity, so minus this goes to minus infinity, and e to the x, when x goes to minus infinity, goes to 0. Do you see that? This is e to the x. This is the y-axis, e to the x, right? So when x goes to minus infinity, goes to 0. Or you can think of it as e to the minus x, right? So this is a 0 over 0 situation. If you try to do L'Hopital 0 over 0 here, what you would get is the following. you would get what? The bottom is going to be 100x to the 99. This is a good start. We reduced the power by 1. Obviously, we're going to have to do it 100 more times, but that's okay. But what about the top? The top, we're going to get e to the minus 1 over x squared times the inner derivative, which is 2 over x cubed. Do you agree? And when we rewrite this, we're going to get the limit as x goes to 0 plus. This e to the minus x squared is still here. This 2 is still here. This 100 is still here. But now we have x cubed and x to the 99, so we get x to the power 102. Do you see that? So obviously, we don't want to do L'Hopital even one more time, because it's going to get the denominator to an even higher power, and we're not getting anywhere. When it looked like it's going to be 99, we could say, okay, we'll do it 99 more times. That's fine. Maybe we'll do 2 more times, see the pattern, and we won't have to write all the iterations. But this is bad. Do you agree? Okay, oops. We're not going to continue this. But here is an example where taking reciprocals does work. So this equals, this is an equal sign. Let's do it like this. This equals the limit as x goes to 0 plus of x to the power minus 100 divided by e to the power 1 over x squared. I just sent the top to the bottom and the bottom to the top. I can do that, right? Do you agree that these two are the same? Do you agree that now it's no longer a 0 over 0 situation, but now it's an infinity over infinity situation? Do you agree? And now it's gonna work. That's slang, isn't it? I'm not going to write the details. Do L'Hopital, do it correctly, carefully. You'll see that you're going to get x to the power 98. Okay? After the cancellations. You're even going to jump 2. And then do it again, 96. See the pattern. The pattern is very obvious. And you can calculate the limit. Okay? The pattern is going to be very, very obvious. So let me maybe tell you equals, so after dot, 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 after you do it sufficiently many times, which in this case is kind of like 50, but you don't actually do them. You see the pattern. What you're going to get is 50 factorial limit x goes to 0 plus of 1 over e to the 1 over x squared. Okay, so that's when you got rid of all the powers in the on top, and this limit is 0. Okay, so complete this. Do it. See that you can do things like this. Okay? So sometimes just taking the reciprocal does magic. More examples. Example number 12. So example number 12, suppose we have something of the form limit x goes to 0 plus 1 over x plus ln of x. Somebody's cell phone is ringing. Please turn it off. Thank you. Limit 1 over x plus ln of x. Do you agree that this is an example of infinity minus infinity? Okay, so this is not a situation where we can directly apply L'Hopital, but we can do things. And do what, for example? So how do we get addition to become, we want a quotient, right? How do we get addition to become a quotient, or intermediate step, how do we get addition to become a product? multiply and divide by? Ooh. That's no, that's not what I want to do here. Well, maybe other things will work. What I want to do is put this thing as an exponent. So e to the power a plus b is e to the a times e to the b, right? E to the power a plus b is e to the a times e to the b. We just made a sum into a product, right? So that's what I want to do. So I'm going to do this as limit, emphasize the dot, of ln, no dot, of e to the power, this thing, 1 over x plus ln of x. Okay, so ln of e to the something is like doing nothing, right? This equals, and that's the reason I did it, lim, x goes to 0 plus, ln of, and now I have e to the 1 over x times e to the ln of x. Do you agree? Okay, so this sum suddenly became a product here. And what is e to the ln of x? Not 1. It's x. So this is the limit, x goes to 0 plus, of ln of x e to the 1 over x. Do you agree?
What you again? I didn't understand this one.
This last step, e to the ln of x is just x. They're inverse functions. E to the ln of something is just a something. Okay? Now what's the limit of x e to the 1 over x as x goes to 0? This is this is example 10. Look here a second. E to the 1 over x over 1 over x. Right? Do you see that that's exactly what's in the parentheses there? So this goes to infinity. So this is example 10. So this goes to infinity by example 10. So ln of something that goes to infinity goes to what? Infinity. So this entire limit is also infinity. Okay? And these standard things are often used to convert all kinds of undefined situations like infinity, minus infinity, 1 to the power infinity. All those convert to L'Hopitalable things via these standard tricks, which are not really tricks. They're just so standard. Okay, but you have to practice them. It's important to practice a few L'Hopitals till you get used to them. Okay? Couple more examples. Couple more examples. So this was what? 12. 13. So 13, suppose you take the limit as x goes to infinity of ln of x divided by x to some power. Let's call the power p for power. Okay? So by L'Hopital, this is an infinity over infinity situation. Let's assume that p is greater than 0. This is an infinity over infinity situation. So I take the limit of the derivatives, of the quotient of the derivatives. 1 over x divided by px to the power p minus 1, which is the limit as x goes to infinity of 1 over px to the p. And as x goes to infinity, the limit is 0. Do you agree? Now, this thing is not just an example. This is saying something. What is it saying? This is saying that when you take a logarithmic function and a polynomial and look at the limit as x goes to infinity, the polynomial wins. Okay, the polynomial wins. The polynomial goes faster to infinity than the logarithm, so the limit of the quotient is 0. Do you understand this intuitive interpretation of this fact? Yes? Okay, so this is saying that polynomials, a polynomial goes to infinity faster than a logarithm. That's this statement that's hidden in this. And this is a very useful fact whenever you go to applications, in particular in studying all kinds of algorithms and how fast they converge and how useful they are and so on and so forth. Okay? And its dual fact, which is our last example for today, is suppose you want to take the limit as x goes to infinity of a polynomial, x to the p. I'm just writing x to the p, but you could, of course, take sums of powers, take an actual polynomial, and divide it by an exponent. Who's going to win? The exponent is going to win. And the way to prove this is say, okay, this is again, p is greater than 0, L'Hopital infinity over infinity. So this is the limit as x goes to infinity, px to the p minus 1, divided by, well, e to the x doesn't change. So if you do this enough times, the derivatives of the top lose power. Well, literally lose powers, right? Do you see that? So after enough iterations, you're going to get a constant on the top. Limit x goes to infinity of some constant. It's going to be what? The p factorial, right? This constant, we even know what it is. It's p factorial divided by e to the x. And again, the limit is what? 0, meaning, okay, so the interpretation of this is an exponent goes to infinity faster than a polynomial. Is this clear? And in fact, I'm going to take 20 more seconds of your time. In fact, if you draw a picture, if you draw e to the x, it looks like this, right? E to the x looks like this. You all know that, right? What does x squared look like? A parabola, right? But if you try to draw them on the same coordinate system, either using your bare hands or using a computer, what you'll see if you try to draw them on the same coordinate system is x squared is not going to look like this. It's rather going to look something like this. This is going to be what x squared is going to look like. It is a parabola, except it's a parabola that somebody sat on. Very, very, somebody heavy. Okay, and the reason is that if you look at, for example, x equals 100, x squared is just what? 10,000, right? Whereas e to the power 100 is something very big. Okay, so e to the x goes to infinity much faster than x squared. That's the graphic interpretation of this fact that we just mentioned. Okay? And similarly, if you draw ln of x and, I don't know, root x, for example. Okay? Okay, so this is L'Hopital's rule, and this is where we're going to call it a day for now. Thanks.